Observatory lecture. I want to thank you all for coming. My name is Donna McCormick. I'm the Executive Director of Montauk Observatory. And I'd also like to thank our co-sponsors, Guildhall, especially Christina Strasfeld, Jen and Joe Rondo, and Anthony Madonna for putting this event together. For those of you who don't know about Montauk Observatory, could you raise your hands? Okay, not many, that's good. But for your benefit, we're a New York State nonprofit that's dedicated to fostering interest in science and particularly astronomy across the South Fork. We have an astronomical observatory that we're still putting the final touches on. That's located on the campus of the Ross School in East Hampton. And we also do lectures like this one across the South Fork. If any of you haven't gotten our events notice, there's a nice list coming up for the summer months. And if you'll raise your hand or go in the back later, you can pick up a flyer. If you'd like to be on our mailing list for event notices, I also have some slips of paper on that you can pick up later. Let's see, what else do I want to tell you about today? Oh yes, Saturday we have another event coming up at the South Fork Natural History Museum. It's called How Small is Small? How to Measure an Atom and Other Things. It's going to be presented by Montauk Observatory board member Sean Tabelia, who's also the chair of science at Suffolk Community College, the Ammerman campus. Very smart, funny guy too. And it's an event more for kids from about 6 up. It starts at 10:30, is it, Carol? Yes, okay. And you have to get on SOFO's website or call them to register. So tonight, we also give thanks to Professor Armitage here, who agreed to come all the way out here from Stony Brook University, Department of Physics and Astronomy, to talk to us about this interesting interstellar visitor that is fascinating phenomena, and we're all still trying to figure out how to pronounce it. I heard there's some side bits going too. But Professor Armitage is originally from Cambridge University, and he's, what'd you say, planetary scientist, interested in the evolution of planets, and he also heads up the planetary science group at the Flatiron Institute, Manhattan. So if you'll join me in welcoming Dr. Phil Armitage.
Thank you very much. Thank you. It's a delight to be out here on this wonderful spring evening, and tell you about this object called, which I'm going to pronounce with an English accent, Oumuamua. Okay. We'll see. We'll see how that goes. And this is an interstellar visitor, and it's maybe something that people have heard about because it's been in the news at least a little bit recently. So maybe raise your hands if you've heard about. So maybe 50%, something like that. And it's I think a fun topic to talk about because it's very new. There's a lot we don't know about it. There's a lot that's mysterious. And it's also something where actually what we do know is sufficiently small that by the end of the evening, you'll pretty much know everything there is to know about it, including some speculations that are not really real. Okay, so let's get started. Some of you have heard about this, so let me just sort of start with a frequently asked question so that everyone's sort of on the same page for the basic picture. So what is or what was Oumuamua? And what it was is the first object which we've seen which unambiguously had an origin outside of the solar system. Okay, so this is a thing, a little rock, a little icy rock probably, which came through the solar system, but which didn't have its origin in the solar system. It came from another stellar system. The name Oumuamua is a Hawaiian word, and it means scout. So it's actually a very appropriate name for this kind of thing. It's the first thing, and it was traveling from afar through our own solar system. What do we know about it? Well, that's the topic of the talk tonight. So we'll go through all this stuff. But basically what we know about it is that it was very small, so it's a very small object. It probably had an unusual shape. You may have seen pictures of it, or artist impressions of it. It looks something like a sort of cigar, perhaps. It probably had a rather unusual sort of rotation state, where it was sort of tumbling through space as it came through the solar system. And at least from a direct point of view, there was no signs of water. So it didn't appear in the solar system like a comet. It looked more like an asteroid. Is it an alien spaceship? That's something that's been in the news. I'm afraid not. So if that was what you came for this evening, sorry. Either that or I'm hiding the secret like everyone else, right? So if it's not an alien spaceship, why is it interesting? Maybe we're only interested in alien spaceships. So it's interesting to me because on an individual level, it's a puzzling thing, okay? And so there's some mysteries which partly come from just the fact it's the first one, and we didn't observe it all that well because it was hard to observe, so there's some puzzles that are really hard to resolve, so that's interesting. But then more generally, it's the first of, let's say, a new class of objects. We don't think there's just one of these. They must be coming through the solar system all the time, and it's likely over the next years we'll discover many more, and they'll give us actually a new way to understand how planetary systems are starting to form. Okay, so this is a talk about Oumuamua, but I want to start actually much closer to home, though still a long way away, with Pluto. Okay, and this is an image of Pluto from the New Horizons spacecraft that flew by Pluto a few years back, and Pluto's this small icy world out of the outer part of the solar system. And the aspect of Pluto that is sort of relevant to this story is that Pluto itself tells us something, or was part of a story that told us something about what went on in the early history of the solar system. And the key here is a puzzling fact about Pluto, which was known from right back when Pluto was discovered, which is that the orbital period of Pluto, which is 250 years, give or take, has a peculiar relationship to the orbital period of Neptune, which is the next planet inside, which is about 165 years. And the ratio of those two orbital periods is 3 to 2. Okay? And this is what we describe as a resonance, and is actually what allows Pluto to have a very unusual orbit, which at the point of its closest approach to the Sun comes interior to the orbit of Neptune. And if you think about that, that's puzzling, because these things have been going there for 4 billion years, more than 4 billion years. Pluto has kept on moving inside the orbit of Neptune, but they've never collided. And the reason they don't collide is that they have this 3 to 2 resonance, which means that when Pluto moves inside the orbit of Neptune, Neptune is never there to collide with it. Okay. So it's a puzzling thing that's been known from basically from when the time that Pluto was discovered. But it was only much more recently, relatively speaking, in the 1990s, that the understanding, the explanation for how Pluto got into this strange orbit was discovered. And that was work done by Rendezvous, who's a professor in Arizona. And her explanation was that Neptune and Pluto didn't always have this strange relationship. And when the solar system was forming, Pluto was probably further away from Neptune and had more like a circular orbit. And the basic picture that Rendezvous came up with was that both Pluto and Neptune were in the outer part of the solar system, and in that region of the solar system there was also a large disk of small bodies, some of which may have been like Pluto, but others which were much smaller. And the idea is that Neptune interacted with those small bodies and basically threw them out of the solar system, or more accurately, threw them inside in the solar system where Jupiter eventually ejected them. And as a result of Neptune scattering that disk of bodies, Neptune's orbit expanded in a sort of fairly slow way. So it didn't happen all at once, but Neptune's orbit gradually expanded, and its gravitational interaction with Pluto eventually captured Pluto into this unusual 3 to 2 relationship of orbital periods. And as that happened, and then as Neptune continued to expand, its capturing of Pluto caused Pluto to have an eccentric orbit, which eventually became eccentric enough that at closest approach it dips inside the orbit of Neptune. Okay. So that's the story, and it's sort of a little cartoon graphic there at the bottom there. It's a picture where the orbital configuration of the planets changed at this early time in solar system history due to the scattering of small objects and ultimately their ejection from the solar system. And the consequence of this theory was the prediction that there should be many other things like Pluto in similar orbits in the outer solar system. Those weren't known in the early 1990s, but they're now what we call the Kuiper belt. Many of them have been discovered since. And that whole story is one of the reasons why many people don't like to call Pluto a planet anymore, because it has all these other objects that share its orbit. Okay, so what does that require? Well, if you want to move Neptune around, you need a lot of mass out there in these small bodies for Neptune to interact with. And what you're watching here is a simulation of the early history of the outer solar system, where you've got the 4 outer planets of the solar system, and then the green dots swirling around are this massive disk of bodies that we think was there at early times. And at some point here, you're going to see there's an instability in the planets, which causes them to expand outwards, and this capture process to take place. That's going to happen about now, all over in a frame or two. So what happens in this kind of story is that there's an instability in the outer planets of the solar system early on, maybe actually much earlier on than was shown in this movie, which causes the planet's orbits to expand, and then this capture of Pluto and so forth takes place during that process. So that's what's called the Nice model for the outer solar system, and it's a popular way of understanding, we think, many aspects of what went on in the early solar system in the outer regions. Okay, so that was the solar system. We think the same thing may have happened in extrasolar planetary systems. Let's just move forward to this next slide. A second. There we go. The same thing may have happened in extrasolar planetary systems. Here there's a movie, a simulation, showing distance from the sun, from the star on the x-axis, or the horizontal axis, and the eccentricity of objects on the vertical axis. And here you've got, in the inner region, a terrestrial planet-forming region where objects are colliding and getting larger. You've got 3 giant planets, which are those big black circles, and then you've got a Kuiper belt further out. And here's another example of a sort of instability taking place in a planetary system, a simulated instability. Here you had an instability among 3 giant planets that basically destroyed most of the terrestrial planet material and also kicked out a lot of stuff from the outer regions. And when we look at extrasolar planetary systems, the reason we think things like this may have gone on is that we see a lot of giant planets, things like Jupiter, that have quite non-circular orbits. And one way to get non-circular orbits is to start with circular orbits and then have strong gravitational interactions among massive planets. And that was what you were seeing in that simulation. Okay, so those are things we think happened in the solar system and in extrasolar planetary systems. And a consequence of them is that we think that during the formation of planetary systems, a lot of material was ejected into interstellar space. Here's an image of our galaxy. This is from the European Gaia spacecraft, their data release of last year. And you can make a sort of simple estimate of how many of these small things ought to be floating out there in interstellar space. So if you say that a star that has, if you like, a solar system-like planetary system ejects maybe 10 or 100 Earth masses of small bodies during the time that it forms, and you combine that with the fact that about 10% of stars, we think, have planetary systems that contain giant planets, the prediction is that per solar mass of stars in the galaxy, there should be maybe between 1 and 10 Earth masses of basically comets and asteroids, or things like comets and asteroids, that have been flung out and are now wandering through interstellar space. And if you put that in numbers, it obviously depends how big they are, but if those objects were about 1 kilometer in radius, the number you'd come up with is that for every solar mass of stars in the Milky Way galaxy, and there's 10 to the 10 solar masses, more than that, of stars in the Milky Way, there would be something like 4 million interstellar objects. So you multiply that 4 million by the number of stars in the galaxy, and you get some truly astronomical number, as you should, because it's astronomy, right? So lots of these things out there. Interstellar space should be filled with the debris, basically, from planet formation, which has been left over. Okay? So there's a lot of objects out there, basically for sure, but there's also a lot of space. Right? That's another basic astronomical fact, right? Space is big. So how likely is it that we're actually going to see one? And Oumuamua is important and interesting because it's the first one that we saw. Okay? So it's the first interstellar object that's been found, and it was discovered with the Pan-STARRS survey in October of 2017. So Pan-STARRS is a survey takes place from Hawaii. It's actually Maui, not the Big Island, and it's a telescope, a small telescope with a large camera that scans the sky, looking looking for a variety of things. It's looking for near-Earth asteroids that might one day impact the Earth. That would be not so good, right? And it's also looking for things like surveys of galaxies, looking for distant supernovae, and so on and so forth. So this was found with pan stars. And here's what its trajectory or its orbit looks like. So here's the plane of the solar system down on the bottom there. You've got the orbit of a sort of typical comet, which is typically inclined to the plane of the solar system. And Oumuamua came in from way out of the plane of the solar system, plunged in towards the sun, passed inside the orbit of Mercury, and then flew out again, sort of roughly in the direction of where Earth was at that time. And it wasn't seen on the way in, or when it was really close to the sun. It was actually first detected already on the way out, and actually that meant there wasn't that much time to follow it before it became too faint to be seen. So everything we know about the object was accumulated in a fairly short period, a few weeks, in October 2017. After that, it moved too far out again in the solar system, headed back into interstellar space, and there were basically no further observations that were possible. So what do we know about it? Well, the thing we know best about it is the orbit. And what we know is that when it was far from the solar system, sort of just approaching the solar system, it had a velocity relative to us of about 26 kilometers per second. So here's a plot showing a whole bunch of comets and other things that we've seen in the solar system. So this is on the horizontal axis how close they get to the sun at closest approach, and on the vertical axis is how eccentric the orbit is. So 0 is circular, 1 is very eccentric, and more than 1 is a hyperbolic orbit, an orbit that is not part of the solar system, not bound to the solar system. And what you can see is that Oumuamua, which is up at the top there, really sticks out from this distribution. There's no doubt whatsoever that it was never part of the solar system and it really was an interstellar object. And if you go back in the astronomical record, there were lots of comets known which had eccentricities just a little bit larger than 1, and which people sort of discussed. Maybe they were, in fact, interstellar objects, but basically it was always within the margin of error. So Oumuamua is the first thing which really, absolutely for certain, we know came from another stellar system. And it was given this name, which is a Hawaiian name. It means leader, as in a leader in a battle or some activity like that, or a scout. So it's really, as I say, a very appropriate name. It's discovered from an observatory on Hawaii, and the first thing we saw, and you could sort of imagine it as a scout from another stellar system. Okay, so what do we know about it? Well, we don't know very much, and the reason is that it was faint. Okay, so even at the point where it was first discovered, when it was brightest, it was a very faint object. So for sure, there was no possibility of resolving it and taking a picture of it. No possibility really of taking, let's say, a high quality spectrum, and even seeing it was a difficult task. So what we know is that its brightness varied over the time that it was observed by quite a large factor. Okay, so this is what's being shown here: the brightness on different days and nights while it was being observed, and it had this sort of complicated, not very regular light curve. And the interpretation of this is that it had a shape that was maybe something like a cylinder, or a rugby ball shape, a football shape, tumbling over in space with some sort of non-uniform rotation pattern. Okay. And how big it is, we don't know. It depends whether its surface was very bright or whether the surface was very dark. Okay. So here's just some sort of typical numbers. It might have been a couple of 100 meters long and a few tens of meters wide. It had a bright surface. Perhaps more likely it had a dark surface, because most things we see sort of the same character in the solar system are pretty dark. In that case, it might have been a kilometer long and a couple of 100 meters wide. Okay. But whatever, it was a small thing. So for those aficionados of science fiction, have seen Rendezvous with Rama, which is a famous Arthur C. Clarke book. This is my copy of it. You can see I was obviously very keen on Arthur C. Clarke as a kid. And that was about an interstellar visitor to the solar system, which was an alien spaceship, and it had about actually the same shape as we think Oumuamua had. So about the same axis ratio of length to width, but the spacecraft in Rama was much bigger than Oumuamua. Okay, that was like 50 kilometers because the earthly astronauts could go and explore it. Okay? So you can sort of think of it as being like the spaceship in Rama, but much smaller. And this thought was perhaps had by other people while the object was passing through the solar system. Avi Loeb, who's a professor at Harvard, and works with the Breakthrough Listen project, which is a SETI experiment to look at other stars for signs of extraterrestrial intelligence, said, most likely of natural origin, but because it's peculiar, they checked whether it had radio emissions. Obviously, none were detected, or you would definitely have heard about it. So, if there were any aliens there, they'd turn their cell phones off while they were passing through the inner solar system. But remember Avi Loeb, because he's going to come back later. Here's a second act in this story. Okay, so going back to what we saw about it, there's something we didn't see. Okay, so when obviously comets come into the inner solar system, they release gases, water vapor, and so forth, and that also carries off dust particles into the space around the comet. And when those interact with the sun, solar radiation, that produces a coma, extended source around the comet, and ultimately a tail. So you can look at Oumuamua and ask, was it really a point source on the sky, or was there evidence for a coma or a tail that would indicate that water was being blown off and carrying dust with it? And nothing was seen. Okay, so to the limit which you could be done, it really was just a point source of light on the sky. And for standard assumptions, so you have to make some assumptions here about how much water was being blown off, or could have been being blown off, and how much dust it was carrying with it. You get a very stringent limit to how much dust was being blown off into space as it came through the solar system. It's really just a few grams of dust per second. Okay, so a really tiny amount of dust would have been seen if it was being blown off in the same way as happens for comets. So what this says is, let's say the straightforward interpretation is that this was a rocky object rather than an icy one. Okay? The rocky object, wouldn't expect to blow any dust off. An icy one would get hot; it would blow dust off. Now, you can also ask, what was the color like? Did it have a color which was similar to asteroids, or similar to comets, or similar to other things we see in the solar system? And there's really not a lot you can say about this. So here are some data of basically the brightness, the reflectance of the object at different wavelengths, different colors of light, here in the optical and the near infrared. And the data points are what we saw for Oumuamua, and the bands here are templates for solar system asteroids. And what you can see here is that Oumuamua had colors that were comparable to some solar system asteroids. Not all, but some. So, from the point of view of the color, it could be similar to some of the solar system asteroids that we see.
I noticed a number of really strong absorption spikes in there, decreases in reflection. Any identifications to what the chemistries might be to that?
Yeah, so I would say nothing here in terms of deviations from a sort of smooth curve is thought to really be very significant. So we don't have anything to say about that. So it could be an asteroid, but then it also has colors that are consistent with some outer solar system objects. So those are icy things that form way out there in the solar system. So here's some a similar set of data and a similar set of bands indicating things in the outer solar system, what kind of colors they have. And you can also find some things in the outer solar system with colors rather similar to Oumuamua. So just from an observational point of view, we don't really have any way of saying it's an asteroid or a comet. It could be consistent with having formed in the inner part of the planetary system, or having been formed way out there.
Was all this data collected just in Hawaii, or?
Oh no! So all over the world, all over the world, which could see this object.
Okay.
Yeah. So it was discovered in Hawaii. There were, quite a few other observations in Hawaii, but there were also observations with the Hubble Space Telescope and other things. Okay, so based on that, and that's most of what we know. The original interpretation, the initial interpretation when this object was discovered, was that Oumuamua is sort of an unusually shaped asteroid which have been ejected from an extrasolar planetary system during the time that it formed. Okay? And if you ask, well, okay, is that kind of shape? The shape seems really weird if it's maybe 5 times as long as it is wide, or something like that. You know, is that consistent with what we see? Does that ever happen? It's unusual in the solar system, but it's not completely unprecedented. In fact, we don't know very much about the shape of objects that are just a few hundred meters size in the solar system, because those are very difficult to see, even if they're local to the solar system. So whether they're typically rounder than that, or commonly have such very distorted shapes, is not something we know tremendously well. Okay. So the other thing you can do that was done back at the time was to make an estimate for how common these things have to be. Okay, and of course, we've only seen one of them, so making an estimate for how many of them there are out there based on a sample of one, is a dangerous thing, and you wouldn't approve it if your doctor, your medicines were approved based on a sample of one, right? But we're astronomers, and so we do this kind of thing very often. Okay, stakes are not so high as medical things. So you can make that kind of estimate, and the number you get is that in interstellar space, if you take a cube that's an astronomical unit in size, an astronomical unit distance from the Earth to the Sun, the number of those objects is about 0.2. So you need 5 of those cubes on average, and you have one object. Okay. Or if you want to put it another way, if you take a parsec, so a parsec is about 3 light years, you have a cube, a parsec on a side, then you're about 4 Earth masses worth of these objects in that volume. Okay. So what that means is actually that unless we were very lucky, unless we really were very lucky, actually these things are not intrinsically that uncommon. Okay. So if you are took the volume of the inner solar system, there are actually probably several such objects passing through the inner solar system at any time, and have been since time immemorial. Okay. And we haven't seen them before simply because they're very difficult to find, because they're very faint and they pass through the solar system very, very quickly. And of course you can also say, well, might one of them one day hit the Earth? And of course in principle that's possible, and perhaps every 100 million years one of them would hit the Earth. So you don't have to worry about that really, because asteroids from our own solar system hit the Earth much more frequently than that. Okay, so we've been particularly unlucky to be blown up by an interstellar asteroid, right? The terrestrial ones are more dangerous. Okay, so that's what we know. So what are the puzzles that this thing poses? So here's the artist's impression of it that you may have seen. It's purely an artist's impression. We've no idea whether it really looked like this, but probably it was sort of elongated, and probably it did have a dark surface. So the first question is, have we been lucky? So I just made a comment about that, saying we haven't been lucky, but that's based on several things. So as I mentioned, it's based on a sample of 1, so that's the first thing you should be worried about, but we'll ignore that. But if you take that estimate at face value, it suggests that the mass of interstellar objects out there is consistent with about 10% of stars ejecting tens of Earth masses or planetesimals each during the time they formed. As I said, we think the early solar system ejected maybe 50 Earth masses of planetesimals, these small bodies. So this is all good. Okay, so this suggests, this is good. And those of us who thought about these problems before Oumuamua were discovered were appropriately happy, right? Because there we go, a theoretical prediction that seems to have been borne out. But it's not so good. Okay, and the reason for that is that you only get this good agreement if the mass of interstellar objects that are out there is predominantly in these small bodies like Oumuamua. Remember, Oumuamua is just a few hundred meters, maybe 100 meters in equivalent spherical size, so it's very, very small. Okay. But if instead you look in the Kuiper belt, in the outer part of the solar system, you've got a disk of objects there that are sort of the things, basically, that we think our solar system ejected early on. And if you look in the Kuiper belt, most of the mass is out there in the largest objects. It's in Pluto and in a relatively small number of other objects, 1,000 kilometers or more in size, that are sort of like Pluto. So of course there are many, many small objects in the outer solar system, including probably things that are the same size as Oumuamua. By number, those are by far the dominant things out there, but they really don't have very much mass. So if you eject 50 Earth masses with a mass distribution that's similar to what we really see in the solar system, then the number of the small objects like Oumuamua is reduced by about a factor of 1,000, or maybe even by more than a factor of 1,000. So that says, we saw one small object. Okay? If we weren't to be lucky, we would have to have an enormously larger population of them out there and an enormously larger mass than that simple estimate suggested. Okay? So maybe we were lucky after all, or maybe, more likely, there's something here we're not quite understanding, right? There's something where our chain of logic has broken down. Okay. Now, you might say, well, what we see in the outer solar system now, objects have collided, they've grown over the billions of years since the solar system formed. So maybe things were different early on. Maybe early on things were in much smaller sizes, and the sun and other stars ejected a lot of small things while they formed, and the big things like Pluto we see today came about later. Okay? So that's a possibility. Work actually that we've done and that we're continuing to do at the Flatiron Institute is to try to model how these small objects formed in the first place. What you're seeing here is numerical simulations of that process, where what we think happened is that when the sun was still young, surrounded by a disk of gas and dust, then within that disk of gas and dust, gravity brought together solid materials and eventually collapsed them into things like asteroids and comets. And the simulations we've done, which is what you're seeing here, suggest that even when they formed, most of the mass in those populations was in quite big things rather than Oumuamua-sized things. So as far as we know, that loophole doesn't get us out of the problem. Probably, even in the early days of the solar system, things were bigger than Oumuamua size, whereas most of the mass was in things that were bigger than Oumuamua size. Of course, we might be wrong about that because these are computer simulations, not reality. We know that there are things that are wrong with those kind of simulations. So we're theorists, so we have a hypothesis for maybe how we can square this circle, how we can get everything to be in agreement. One possibility is that perhaps planetary systems really form quite large objects, but in the act of throwing them out into space, or ejecting them into space, they get broken up into smaller pieces. Okay? And that's a process that we know can happen because we actually saw it happen in the solar system. So some of you will remember this. Maybe not the youngest members of the audience will remember this, but a number of years ago, a comet, Shoemaker-Levy 9, came close to Jupiter, and it was broken up, as you can see in this lovely image, into this string of pieces, beads on a string, as it were. It was broken up by the tidal gravity of Jupiter. And the pieces went on to impact Jupiter, for the most part, and they produced dark spots and so forth on the surface of Jupiter where they impacted Jupiter's atmosphere. So the same thing could have happened in extrasolar planetary systems and in the solar system, and the objects that were broken up don't have to hit the planet, they can be ejected out into space. Okay? So it's possible that as planetary systems are ejecting things, they're actually grinding them down into little chunks, and Oumuamua is one of those little chunks which has been flying out there. Okay? So we've played with that model. Sean Raymond, who's a collaborator of mine in France, has actually a nice blog where he discusses this and a whole load of other cool stuff. So if you're interested, you can see more about it. We think the numbers might work, but it's by no means guaranteed. So it's a possibility, but not by any means the answer to the problem. Okay, so that's one puzzle, and then there are other puzzles about its composition and its orbit. Okay. So I already mentioned that we didn't see any sign of dust or gas. Okay, so the simple interpretation then is that we're dealing with a rocky body, something like an asteroid, rather than an icy one like a comet. So that's a puzzle in itself, because if we think about the solar system, there's more mass. We think there was more mass, particularly in icy objects far out from the sun than in rocky ones. So here's the inner solar system. So there's the asteroid belt swirling around there. The asteroid belt has very little mass today, and we think that even early on, when it was much more massive than it was today, it was still much less massive than this primordial disk of icy objects that we think was out there beyond Neptune and including Pluto, and tens of Earth masses of things like Pluto. Okay. So we think there was less mass in rocky objects, and then even even apart from that, because the asteroid belt is much closer to the sun, it's much harder to eject stuff from the inner solar system than it is from the outer solar system. So it's hard actually to throw it back out into space as well. So it would be a surprise from a sort of theoretical point of view if the first interstellar object we saw was actually rocky rather than icy. So we have an idea for that one too, okay, which is the dry skin solution. So we're taking an inspiration here from advertisements, and the idea is that Oumuamua perhaps started out as an icy object, was an icy object, but of course icy objects in the solar system and elsewhere are not made of pure ice, right? They're not beautiful ice like you have perhaps for ice cubes. Okay? Instead, they are icy in the main, but they have a lot of rocky material mixed in there. I've heard of the description of comets as being dirty snowballs, right? So there's a lot of solid material, rocky material mixed in there. So there's a possibility that you could start with an icy object and then lose water from the surface, perhaps in the planetary system where Oumuamua formed, or perhaps, conceivably, as it passed through space on the way to the solar system. That second one is a little bit harder for various reasons. So what would happen then is that water would be lost from the surface, leaving a sort of rocky crust, and you just have water in the middle of the object. So then what does that mean? Well, then as you fly through the solar system at very high speed, the crust there actually acts as a sort of insulation to the interior. So even though it's being heated very strongly by the sun at the point of closest approach, the ice doesn't get hot enough to sublimate and turn into water vapor. Okay? So you keep the interior cool by having this insulating layer on the surface. And something that surprised me, because I've never thought of this kind of problem before, is that you don't need much of a crust to provide enough insulation. So you might say, here's this object getting inside the orbit of Mercury, it's being tremendously heated up by the sun, surely the interior must get hot enough. But actually you can find that maybe a meter of this crust, if it's rocky, gives you enough insulation. So the surface gets hot, but just a meter down underneath, it doesn't get hot enough to vaporize the water. So that was a possibility, and it appeared to receive some support by observations that came a little bit later. So as Oumuamua was leaving the solar system, its position was measured with the Hubble Space Telescope. And what was found there was that the trajectory was not exactly that of just a point gravitational mass moving through the solar system under the gravitational influence of the sun and the other planets. Actually very slightly deviated from that at a very significant level. So we really think this is what happened. So in addition to the gravitational acceleration, there was actually a small extra acceleration which could have been caused by small jets of water vapor blowing off the surface and giving a little force. And that's what's shown on those plots at the top. The one on the left is how well the observations fit the data in the case of no outgassing, so no water coming off Oumuamua. On the right with this very weak outgassing, similar to a sort of comet, but much weaker, which gives a little force that makes the observations fit the data, makes the model fit the data much better. So this is not intrinsically surprising, because we actually see jets of vapor coming off comets basically all the time, or we see it affecting their orbits all the time. And then the European Space Agency's probe Rosetta, which tracked a comet as it came towards the inner solar system, made this little movie up on the left there, and you can see this stuff jetting off the comet very clearly in those images. So the picture would be, there's Oumuamua. It's not producing a lot of water vapor, because if it did, we would have seen the dust and so forth. But maybe it's producing a little, and that's enough to give it this little extra boost in its orbit. Now, I should say there's a problem with this solution to a problem, which is, here imagine you have Oumuamua and it's got this cigar-like shape. Suppose the water jet is off at one end. Okay, so then you've got this sort of long cigar-shaped object, and you've got a thruster on one end of the object. Okay? Well, if that is the case, then it gives a force to the object, but it also tends to spin it. Okay? So if you just have one or two jets, and they're sort of randomly placed on the surface of the object, they would tend to spin it up like a top, and because it's very weak, it's a very small object with not a lot of gravity, they would have actually spun it up enough that it would have just broken up into pieces, before it got to the point where it was observed. Okay, so there's some little issues there, possibly larger issues, about being able to get the force you need to explain the orbit through the solar system without spinning it up and breaking it up in the process. So, because of that, there was this additional thought. So we go back to Avi Loeb, who, remember when Oumuamua was actually in the solar system, was discussing whether there was radio emission and looking for radio emission there. And based on this idea of the orbit not being the supply that of a point mass, he asked, well, could the extra force on Oumuamua that we actually observed, the deviation from a simple trajectory, be due not to water being blown off the object, but due to the pressure of sunlight on the object? Now, of course, the sun, radiation from the sun, is undoubtedly exerting a force on everything in the solar system, right? So there's no doubt that effect is there, but it's a very weak effect. Okay? So small objects in the solar system are affected a little bit by radiation forces, or at least thermal forces that result from that radiation, but they're affected very, very weakly. So if you want to change the orbit of something flying through the solar system, and it's just going through in one pass, due to the pressure of radiation, what you need is a big surface area and very little mass. So you get a lot of acceleration for the amount of force you give. Now we know the size of Oumuamua because we see its brightness, so we can't change that. So the only way we can do something with radiation pressure would be to make the mass very small. So that means that instead of being a cigar, it would have to be a sheet, basically. Okay. So that's the idea there. It's a sheet material. We don't think there are any ways of producing wafer-thin sheets naturally. So the only thing would be to make it artificially. It would be a light sail from an alien civilization, which happens to have gone through the solar system. It's therefore very, very light, and it gets this non-gravitational acceleration. So paper was published on this, some stuff up there. Origin could be either natural in interstellar medium. I think it's really very, very unlikely that you can do that, or artificial. So that's the basis of what you may have seen. Some of you may have seen this discussion that this was an alien spaceship, a light sail. It's based on this non-gravitational orbit and making some assumptions about that. Now, at this point, astronomers go back to Sagan, who popularized the saying, which I said before, that extraordinary claims require extraordinary evidence. Obviously, we don't have. Well, this is an extraordinary claim, and we certainly don't have extraordinary evidence here. In fact, we don't really have any evidence actually. So it's a fun idea, but I think basically we can cross this one off. And so go back to my frequently asked questions. It wasn't an alien spaceship, unfortunately. Right? Actually, very fortunate, right? Because it would be super sad if the first alien spaceship to pass through the solar system didn't say anything, right? It's like incompetent aliens who haven't got their spaceship working properly if they just fly through and don't say anything to us. Okay, so this is just the conclusion. What have we learned from this object, Oumuamua? So the thing we've learned directly, to say, with the caveat that we might have been really lucky, is that small interstellar objects are really surprisingly abundant. So I didn't say, but people thought about this possibility before Oumuamua was found, and it was thought unlikely that even the Large Synoptic Survey Telescope, which is a much more ambitious sky survey that's coming online in a few years, it was thought unlikely that LSST would find even one of these objects. So the fact that one was seen earlier with this basically precursor survey, Pan-STARRS, was a big surprise. Properties of the first example have these puzzles, and they're puzzles that basically we're not going to resolve because it's gone, there's no more data to be taken, and even though I'm a theorist, one has to admit that ultimately when you have puzzling things, you need more data to resolve them. So they're going to remain a puzzle, and we're not going to be able to really answer them. But we will find more, almost certainly, and possibly in the relatively near future. And when more are found, they will really provide a new probe of the way that these small bodies form during planet formation. And that's very important for people who are interested in planet formation like me, because in the solar system, we can observe things tremendously well in the solar system, but we can't get away from the fact that there's been 4.5 billion years since the formation of the solar system for small objects to collide and basically get messed up. So way out there in the Kuiper Belt, we can see some primordial objects, perhaps like the one that was flown past by New Horizons on New Year's Day. But getting to the outer part of the solar system is not an easy task either. So seeing these kind of objects in large numbers will really be a new thing. And go back to the science fiction. The end of Rendezvous with Rama is that the Ramans do everything in threes. And so the projections for LSST, this much more ambitious sky survey, new telescope is being built in Chile for that. The mirror arrived in Chile, I think just yesterday, so it's really well underway, that construction. Those projections, which were previously very pessimistic, have now been revised to at least one similar object per year. So we ought to have a decent sample, not a huge sample of these things, fairly soon. Could we rendezvous with such an object? At the moment, that would be challenging because you don't get very much warning. Okay, so there's not time to build a new spacecraft and launch it. But there is actually a European proposal to build a spacecraft and basically put it out into space in a parking orbit, just waiting for this kind of thing to happen. And that's at the moment proposed to rendezvous with a long period comet, a comet from the solar system, entering the solar system, the inner solar system for the first time. So it's a real idea, let's say. It's not funded yet, but it's a possibility. And so if it turns out these objects are common enough, it's not in principle impossible. We could actually make a flyby of one and really see what it looks like. So I will stop there and take any questions.
Why isn't it more likely that this object will not be captured by one of the already existing objects in our solar system, by the gravitational field of one of those objects?
Yeah, so basically it's moving too fast. So
Moving too fast.
Moving too fast. So to capture it, you need a combination of things. You need, first of all, it to move close to a planet, and then you need to have the right geometry basically. And so something that's really comes into the solar system with a huge velocity, there's basically no dynamical way it can get captured. If it was coming in with a very low velocity, then there would be a chance. But with this 20-30 kilometers per second, even if it went pretty close to Jupiter, it would still keep on going.
A second separate question. How is this different than what might have been the meteor that fell into the Yucatan centuries ago?
Right. So that would have come from the solar system.
How do we know that?
We don't know for certain, but just on the balance of probabilities, impacts with let's say 100-meter sized objects maybe happen on Earth once every 100 years, something like that. The estimate for these kind of things would be that this would happen once every 100 million years. And so the Yucatan thing was much bigger, but the same sort of balance would apply.
The idea of space and interstellar space, and you said there the cube that you created by light years, light year cube. What was it? 4 light years or
Yeah, three light years or whatever. Yeah.
And you said there was about 100 Earth-size masses in that area.
Yeah, I mean,
We could
a
assume-
few Earth masses worth of this stuff. Yeah.
And did you also say that the sizes of things tends to lean towards larger objects or smaller objects?
Right. So let's be careful about this. So
Yeah.
it's confusing, right? So if you pick a random object from this population of things, it will be a very small one. Right? It will be almost as small as it can be, unless you're very lucky. But if you ask where most of the mass is in the bigger objects. So there's sort of that balance. Actually, pretty much every population of small objects we see, by number, the small ones are the most numerous. But if you ask, well, where's most of the mass, it's just in the handful of the biggest things.
And we're only talking 10 to 100 Earth, 4 Earth masses,
Yeah.
right?
Right.
So we're talking about very little mass in a very large cube,
Yeah. So
like
it's
very,
yeah, so if
like
you,
unimaginable.
yeah. So if you a parsec, 3 light years, is about the distance to the nearest star. Right? So roughly speaking, in our galaxy, there's sort of one solar mass of stars in that volume, and then there's a few Earth masses of these little things. So that's a ratio of about a factor of 100,000, something like that. So it's it's a very small amount of mass compared to stars, but it's a lot of objects. So that's how it is.
Although, is there any chance that the object may have come from the Oort cloud?
Right. So no, it couldn't have come from the. It could not have come from the Oort cloud. So the Oort cloud is, this sort of hypothetical region for the long period comets. So an object that comes from the Oort cloud, it's generally perturbed just a little bit by a passing star to come in. So when it comes to the inner solar system, it has a high velocity, but this 20-30 kilometers per second that Oumuamua had would be the velocity it had basically as it passed through the Oort cloud. So that's basically how we know it's interstellar, that it had a much higher velocity at large distance than the objects that do come from the Oort cloud. So the only thing you have to ask is, could it have gotten this high velocity, say, by interacting with another planet? And for sure, it didn't get it from interacting with Jupiter, which is the only thing we know of that could do that. I suppose you could imagine that there was a very massive planet way out in the solar system, far beyond even planet 10, planet X. If that was out in the Oort cloud, then something like that would not be inconceivable. But it'd be, I think, very unlikely. Let's say.
Just one last point about the artificial origin. Our own Voyager probes, 1 and 2, by the time they enter the next interstellar system, will be inert. So the argument that what civilization was sending a defective aircraft or spacecraft, that's us. We're doing it right now.
That's true. That's true.
And
It's
it's
very
possible
true.
that in their journey they could accumulate micro dust and become unrecognizable even to us by the time they reach another solar system.
For sure. I mean, I guess what one would say about that is that Voyager will basically not pass near anything for a tremendously long time. So this object actually came very close to the sun. So if it's natural, so I think it's natural, then basically that's just the selection effect, right? That many objects that are coming through the solar system, some are close to the sun, some are far off. The ones that are close to the sun like this are the ones that are easy to see, right? Unless, presumably if you imagine an artificial origin, then those objects are unbelievably rarer than the natural ones. And so then the fact that it came so close to the sun would have to say that it was really aimed at the solar system. So in that case, it's something that's not just a random thing floating through the galaxy, it really was pointed at us.
Like, what's the difference between this, like a comet? A comet has a lot of things, or more mass, or tails, and things like that. What would this be like? The difference between this be like a dried up comet?
Yeah, so I think that's the most likely scenario. It's a smallish dried up comet.
Does it have an orbit then?
I guess all we really know is, we know where it came from and how fast it came. Okay, you can ask, if you trace it back, did it sort of come from another star that we can identify? And the answer is not clearly. Okay, and that's not really surprising because probably, basically some large fraction of stars, tens of percent of them, have ejected these objects. And so the galaxy has just been really filling up with them since the time the galaxy started. And so it's most likely that you'll see one that has been around for, been floating through space for billions of years, and there's no way of pinning down which other star it actually came from. But people have tried that exercise, right? People have looked, did it point back to some nearby star system, and there's no evidence that we can identify that.
Did it leave the solar system in order to escape velocity, get out of the solar system?
Yeah.
I assume so.
Yeah. So it left the solar system at basically the same speed it came in. So yeah, it will be. At the moment, it's still in the solar system, right? So it takes some time to get out there, but it will leave the solar system with 25 kilometers per second velocity.
So I'm just curious about how come the telescope that picked up the object leaving never picked it up coming?
Right. So it's just luck. So pan stars and these future surveys are basically trying to cover the whole accessible sky from whatever location they're at, and they have some strategy of, taking tiling in the sky. So when LSST is online in a few years, that will be basically covering the entire skies visible from Chile every couple of nights, something like that. Pan-STARRS isn't quite that efficient, so it's just luck. I mean, one thing to say is that actually it's really hard to do this because these objects are coming through so fast that from night to night it changes its position on the sky completely. So the techniques for finding these kind of finding asteroids are to take images and look for moving objects. But something that's moving this fast can easily be missed because it actually just moves off the camera in a very short period of time. So it's actually quite amazing, really, that they were able to find it.
On those images that you were showing, I noticed some small dots. I assume those are stars or other objects, and the little streaks. I assume streaks of the sun.
Yeah, so let's find it. Yeah, so the image on the left is, if you like, the first image where you're tracking on the stars and you see Oumuamua as a little streak. The one on the right is where you track on Oumuamua and then the stars become streaky. So I guess the one on the left, going back to the previous question, shows why it's hard to see that thing, right? Because it's moving very quickly and it gets blurred out, if you like, just by its motion relative to the background stars.
So when we get to Mars, would you say we'll be able to find more of that, or doesn't, space is so large that it doesn't really matter where we are?
Yeah, it doesn't really matter where we are. So we can do, now we know they're out there, we can do a little bit better at finding them. Okay, so I said this was sort of a serendipitous discovery, really. But the sun is actually sort of moving with some velocity relative to the local stars in the galaxy. And that means that these Oumuamua-like objects probably approach the sun from a preferred direction. And it's not a very strong effect, but it is an effect. So if you know that, you could in principle sort of tailor your observations to sort of look at the pieces of sky where you're most likely to see things. So there's some discussions about how to do that, and that's not going to make it 10 times easier to find them, but it will be some kind of an effect. And I think given all the interest that this one has stirred up, it's likely that these future surveys are going to be really looking for them to the best extent they can.
One more. So the telescope that found this, no other telescope saw it? I mean, does it tape anywhere that, I can't believe that this is the only one that saw it.
So this was the only one that detected it. This was the one that detected it. After it was detected, it was observed with many telescopes. But so actually this is sort of part of a sort of ongoing thing in astronomy, right? Which is that we're actually not very good, or haven't historically been very good at picking up transient things in the sky. Right? So we're very good at observing things we know are there, permanent features, but looking for asteroids, looking for comets, looking for supernovae, those are things where you need to image a huge fraction of the sky repeatedly, and then you need to analyze this enormous data set to see something that's changed. So there's actually only a few telescope surveys that are really working at the moment that can do this kind of thing.
And the idea of the parsec mass is an illustration of why it might be so hard. But what is did it stay here long enough? Did we get enough information to learn anything about, like, does this make any difference to our scientific understanding of the universe or our solar system? Or
I mean, I guess I would say there's a long history in astronomy of the first object you see not being a typical. And a mistake astronomers frequently make, or not a mistake, something that happens is that a class of objects is named after the first one, and then decades later when you like teach an undergraduate class, you have to painstakingly explain that the first one wasn't really what the whole class was named after. You know? And this happens all the time, and it causes a lot of confusion. So I think I'd be very careful to say that, you know, it was the first one. Until we really know if it was typical, it's hard to say. If it turns out that, you know, most objects are like this, what it will be saying is that, you know, we didn't understand something, or we haven't understood something about basically the size distribution of objects during planet formation. That, you know, there was a huge number of really small objects that somehow stuck around or were formed that we didn't expect. So a few more of them could make a big difference. You know, it's possible that the next one will look completely different, and then, you know, so it has that potential to make quite a significant difference.
There's a lot I'm missing, so I want to just, we know it's interstellar because of the speed and the angle of attack, essentially.
Yeah,
Is that how we know it's okay?
And, you know, I would say it's the speed which is the strongest argument.
Is it strong?
Speed is the strongest.
You said that greater than one, you know.
Yeah,
it seems
because,
way up.
yeah, so, you know, there are comets, you know, comets from the Oort cloud, going back to the previous question, comets from the Oort cloud basically come at us from all directions. So the comets that we see are sort of have two origins. Some basically come from a sort of disc-like population, and so those are not completely flat in the plane, but they are tilted. But then the ones that come from really way out there, the ones that are coming to the solar system for the first time, those in principle could come from anywhere. So just seeing something coming from a, you know, crazy angle isn't enough. It's the velocity.
You're saying that it, like 20 to 30 kilometers per second is fast. So what are some slow objects? I mean, it doesn't seem that fast to me.
Right. So I should have clarified that. So that's the speed at way out there, right? At thousands of astronomical units from the solar system. So formally, that's the velocity we say at infinity. Okay? So as it actually passes through the inner solar system, it was moving faster than that because, of course, it accelerated as it came towards the sun. So, you know, it moved much faster than that past the Earth. But this is the speed it was at large distances. So it's sort of similar to the random speeds of stars in this region of the galaxy. So which is sort of what you expect, right? Something coming from interstellar space, it sort of has a speed that's characteristic of just a random star somewhere in this part of our galaxy, relative to the sun, and that's a number of, you know, tens of kilometers per second. So it's a big speed for at infinity. It's not a big speed in
Is the speed similar to a shooting star we'd see?
Well, so those would be coming from, you know, things sort of local to the solar system.
Right.
So it, you know, I guess if bits of this had hit the Earth on its way through, they would have been moving faster, a little bit faster, somewhat faster than a typical, you know, local asteroid or comet, because it has this big speed far out. So it's a little bit, but yeah, bigger. I mean, I guess you could think of it that, you know, something that kind of came into the inner solar system from our own solar system, and, you know, came to the Earth, right? The Earth's speed is about 30 kilometers per second around the sun. So if something came and hit us from the other direction, right? You could basically be adding up two of those. So something from our own solar system, in principle, could hit the Earth at, you know, 40, 50 kilometers per second. This object, you know, would have a similar velocity. So it's not so different, simply because everything speeds up in the inner solar system.
So you say that this is so much faster, but faster than what? Faster than a comet or faster than a meteor? Or?
So it's faster than a solar system comet would have when it was way away from the sun. So if you like, imagine the Oort cloud. The Oort cloud is this enormous cloud of comets, where most of the comets come from, the long period ones, right? So that's maybe 10,000 or 100,000 astronomical units from the sun. And so when I say it's fast, I mean that basically as Oumuamua came through the Oort cloud, it had a velocity that was really large relative to the sun, relative to those comets. So that's really the